So to get the determinant of this value, so you have to subtract this one minus this element minus this element minus this element, which is 6.3697 minus lambda multiplied by 18770 minus lambda minus of 331.8 multiplied by minus of 331.8, and this is equal to 0. So that's how you get the lambda value. So if you expand this one, I already did the calculations to save some time. If not, this video will be too long. So if you expand this equation, you will end up with a quadratic equation that will look like lambda squared minus 18776.36 lambda plus 9467.4039, that's equal to 0. I put up to 4 decimals. In the final exam, you can stop up to after 2 decimals. That should be enough. So now we have a quadratic equation. So from here you have to get the eigenvalues. So this is a equation of the form it's a quadratic equation, isn't it? Something like ax squared plus bx plus c, that's equal to 0. So you can find the solution of this equation, which is lambda is equal to minus b plus plus or minus square root of b squared minus 4ac divided by 2a. So here we have what we have here. Here a is equal to 1 because ax squared, no, we have lambda squared, and which means a is equal to 1, and this is b is equal to minus 18776. I can write this up to 4 decimals, so 3697, and then c is equal to 9467.4039. So that's your c value plus c, that's equal to 0. So we can implement the formula to get the lambda values, or the so-called the eigenvalues. So lambda is equal to minus your b value is this is a minus 18776. So minus 18776.3697 plus or minus square root of minus 18776.3697 the whole square minus 4 into a value is 1 into c value is 9467.4039, the whole divided by 2. A is nothing but 1. So lambda will be equal to minus into minus will become plus 3697 plus or minus, you just expand this equation, so that will be 35255.1, some big number 993.1. The exam you are allowed to use the calculator, so you don't have to worry. 37869.6156, the whole divided by 2. So we're almost there. So now we have to calculate the lambda value from here, so which is lambda is equal to 18776.369997 plus or minus square root of, subtract these two values, that should give 3525 14123.5 divided by 2. So this value is square root of what? Square root of this value is approximately equal to 18775.3612. So plug in that value here. So that way lambda will be equal to 18776.3697 plus or minus this value divided by 2. So you will get two values, isn't it? Yeah, one is this value plus this value by 2. Another one is this value minus this value by 2. So you will get two lambda values. So lambda will be, let's say, one lambda value will be 18775.8654 and another value will be 0.5042. So here you have to check which one is the highest value and call that one as the lambda 1 and lambda 2. So make sure lambda 1 is greater than lambda 2. If we have three variables, we will get three eigenvalues. In that case, we have to arrange in the descending order. Yeah. So the highest value will become lambda 1, the next highest will become the lambda 2, and the next highest will become the lambda 3. So in this case, we started with two variables. We started with only two variables. So which means you will get only two lambda values. You get lambda 1 and lambda 2. So now we have to get, so if you go back to the diagram which I showed you a long time ago. So when you project the data, something is falls on this component, another one falls on that component. To know how much percentage is captured on this component and how much percentage of the variance or the percentage of the information captured on this component, how to get that value. So we have to do, you can use the eigenvalue to get that information. So sum this value that should be, if you add these two values, you will get 18776.3696. And now we calculate the, okay, another thing I forgot to mention is, so if this is your lambda 1, so this will become your first principal component. So this will tell about the information captured in the first principal component. So info captured in PC1, and this can be used to calculate the percentage info captured in the second PC or PC2. So let's calculate the percentage information captured, or the correct terminology is the percentage variance captured. The percentage variance is captured in PC1. This is something that we calculate based on lambda 1 divided by lambda 1 plus lambda 2, which is equal to 18775.8654 divided by 18776.3696 multiplied by 100. So what do we mean by that? So this means, so the first component itself enough to capture 100% of the information, or 100% of the variance in the data. So it can capture up to 99.997% of the variance or the information in the data. So which means only one component can capture till about all the information that exists in the data. And what will happen to the PC2? So PC2, the percentage, how much information it captures. So typically it will be 100 minus this value, yeah, the information captured in the first component. So we, but something we can check that 0.5042 divided by, so this is lambda 2 divided by lambda 1 plus lambda 2. So this is 18776.3696, which is multiplied by 100, sorry, it is approximately equal to 0.003%. So when we add both, you will capture 100% of the variance in the data. So if you plot, say like, so what we have here, so if we started with two variables, x and y, and we end up with two principal, which means we can get two PCs, PC1 and PC2. PC1 should correspond something to lambda 1 and lambda 2. So that's something tells about the percentage of the information captured in each component. Yeah. So this is what we did until now. So now we have to calculate. So we know that the first component can carry 99.997% of the information. So where that component lies, say we already have this data. We have this data. Say if you plot this on x and y, so where that component lie, you know, so which mean we need to find the direction of the vector, this vector, and the direction of this vector. So how to do that? So for that we have to make use of the, so what do I mean by that is, say like, you know, one component, so this is your first principal component that captures 99% of the information, and the remaining component that captures only 0.003% of the information in the data, and the total should be 100%. We need to find where this line exists or where the vector exists. So to find the direction of that vector, we need to calculate the eigenvector that corresponds to lambda 1 to get this line, and to get this line or the direction of this vector, we need to calculate the eigenvector of the lambda 2. So the eigenvector of lambda 1, that's nothing but the direction of the principal component 1, and the eigenvector of the PC2 or lambda 2, that's nothing but eigenvector of that corresponds to the lambda 2 is nothing but the principal component 2 or the direction of the PC2. Yeah, so that's, I will explain later how to plot these ones. Yeah, so but for the moment, get the concept. Yeah, that's really important. So from lambda 1 we get the corresponding eigenvector, and then from lambda 2 we get the corresponding eigenvector. That tells something about the direction of the eigenvector, where the projection of the data will carry 99.9% of the information in this case, and where we project the data onto this vector, it will carry 0.003, which is almost no information about the data in this component, or something called as the PC2. So let's calculate the eigenvector that corresponds to lambda 1 and the eigenvector that corresponds to lambda 2. So again we have to apply some mathematical rule or the formula in order to get the eigenvectors. Okay, so I'm going to first calculate the eigenvector for lambda 1 and then for lambda 2. The formula to get the eigenvector is, so we are going to calculate the eigenvector for lambda 1, 18775.8654, and the formula is s minus lambda I multiplied by v, which is the vector, which is equal to 0. So we know this value, we already calculated, 6.3697 minus lambda and 331.8 minus 331.8 minus 331.8, and here 18770 minus lambda multiplied by v1 and v2, that's equal to 0. So v1 and v2, this is nothing but, so if you have starting from, if you have a coordinate something like x and y, and say this is 0 comma 0, which is your origin, so v1 and v2 will be a point somewhere here, v1 and v2. If you connect these two, that will be your the direction of your principal component 1. So we know the lambda value is already 18775. So let's plug in this value here. So which means minus 18775.8654 minus 331.8, and then here minus 331.8, and this value 18770 minus lambda value is this value 1. So that's the value we have multiplied by v1 and v2 and set this equal to 0. So that's the method to get the eigenvectors. So I already subtracted these values. I will write it here for you. So minus 18769.47 and minus 331.8 minus 331.8, and if you subtract these two, you will get minus 5.8654 into v1 multiplied by, sorry, v1 and v2, so that's equal to 0. So now we have to do the multiplication. So let's do that. So you will get, so follow the process, you will get two equations. So minus 18769.4957 multiplied by v1 minus 331.8 multiplied by v2, that's equal to 0. That's one equation. And then this one minus 331.8 multiplied by v1 minus 5.8654 multiplied by v2 multiplied by v2, so that's equal to 0. So you have two equations. From there you can solve for v1 and v2, isn't it? Yeah? So how to do that? So we can write this equation, for example. So minus 18769.49571 v1 equal to 331.8 v2, or v1 is equal to 331.8 minus divided by 18769.49571. So I just put this value to the denominator, or v1 is equal to minus 0.017675 v2. So now, so what we have here, so if we choose, let's say v2 is equal to 1, then v1 will be equal to this number, isn't it? Minus 0.17675. So the v1 and v2, I mean the vector v will be equal to v1 v2, so which means that should be equal to, so v1 is minus 0.1767, I mean 0.17675 and then 1. So that tells something about the vector. So what's um, and normally what we whenever we have this type of value, we try to normalize this value. So how to do the normalization? Normalization is really simple. So normalization of vector, so v is equal to, so many software normalize the calculated vector, so that's what I'm doing now. So normalization is really simple, which is v1 divided by square root of v1 square plus v2 squared, and then v2 divided by square root of v1 square plus v2 square. So why do we do that is because if you go back to the previous step here, so I just put a value when v2 is equal to 1, when v2 is equal to 1, you get a v1 is equal to this number, isn't it? Yeah. If I put v2 is equal to 2, then you will get exactly the double of this number, isn't it? Yeah. So what do I mean by that? So say like so that's our origin 0 comma 0, and let's say if I put v1 is equal to 1, and then if I get v2 is equal to say 2, so that will be somewhere around here 1 comma 2, and if I put, in that case, if I put v1 equal to 2, then v2 I may get 4. So if you draw a line, sorry, it will be around here, what it says is no matter whatever the points that you assume to get these 2 points, which allows you to get the vector. So here what I did, if in the previous step I just assume v2 is equal to 1, and then I get the corresponding v1. So we can do the same principle, no? So here if I put v1, assume we get 2, then if I put v1 equal to 2, then I will get v2 is equal to 4. So what I mean by that, irrespective of the value I assume, the direction doesn't change. Yeah? So I can, if I put 3, then I may get 9, so which will be here. It will lie in the same line. Yeah, so everyone can use a different method in order to get any point on this line. You know? So normalization means whatever the method that we calculated, now I may assume a starting value of 1, you may assume a starting value of 2, but irrespective of whatever the value we use to calculate, if we normalize, we all should get the same value, isn't it? You know? So which in this case 0 point. So minus 0.17675, the square root of v1 square plus v2 squared, and then again we use the value of v2, 1 divided by square root of v1 square plus v2 square. I already calculated this value, so you should get a value of minus 0.017672, and then here 0.999844. So that's nothing but that's the direction of PC1 where the variance is maximum. To be specific, where we captured, let's go back to our calculations. In this PC, we captured 99.997. So this value, 99.997% of the variance in this direction. So this will become the PC1. So typically this will be, if you want to plot it in a graph paper, say this is 0 comma 0, so this value will be, so 0.00017672, so that's almost on the negative side, no? So this is x, That's y, so that's almost here, closer to 0. And then y value is 0.999, so let's say this is 1, so this value will be around here. So that point will be minus 0.17672 comma 0.99844. So if you connect these two points, so that will be our PC1, and typically PC2 will be exactly perpendicular to this one. Yeah, so you may get some value which is completely perpendicular to this, somewhere around here, if you really plot. Yeah, so the line perpendicular to this one will be your PC2. We can calculate the coordinate that corresponds to PC2. So to calculate that, you have to calculate the eigenvector of lambda 2, which is equal to 0.5042. So and again you have to use the same formula, S minus lambda 2 into I multiplied by V, which is a vector. This should be equal to 0. So that's something you have to calculate in order to get the direction of the second component, where we already know that the percentage information captured is minimum, which is around only 0.003%.